Look at a modern submarine operating deep underwater, and you are looking at a completely self-contained, closed-loop survival habitat. Every square inch of its design is a constant, unforgiving negotiation with the extreme physical properties of the deep ocean. The first and most immediate threat to any object entering this environment is hydrostatic pressure. At sea level, we experience about 1 atmosphere of pressure, but as you descend, the sheer weight of the water column above compresses. For every 10 meters you drop, the pressure increases by exactly 1 atmosphere, or about 101.3 kilopascals. At a depth of 1,000 meters, a vessel is squeezed by over 100 times the atmospheric pressure we feel on land. This compounding weight creates a massive crushing force directed inward on any hollow object attempting to penetrate the deep. Before a submarine can fire a torpedo, run a scientific survey, or even steer, it must first be engineered to simply survive an environment that is actively trying to crush it. Avoiding a structural implosion is only the first problem. The second constraint of the ocean is its electromagnetic opacity. Seawater rapidly absorbs and scatters electromagnetic radiation. The signals that run the modern world simply cannot penetrate the surface. This physical limitation means standard GPS positioning, radar, and high-frequency radio communications fail completely at depth. Once a vessel submerges, it is severed from the outside world, forced to operate completely blind. To operate under these conditions, whether as a military predator or a deep-sea research vessel, a submarine must be a fully autonomous system, capable of calculating its own depth, position, and environment without a single byte of external data. The engineering solution to this environment starts with a structural response to hydrostatic pressure. Modern submarines use a dual hull architecture. A highly sealed inner pressure hull is surrounded by a streamlined outer light hull. The outer hull isn't designed to resist pressure, just minimize drag. Water freely floods the space inside this shell, flowing around the inner chamber. That inner pressure hull is where the crew and critical systems reside. To survive crush depth, these hulls utilize highly specific geometries, typically spheres or cylinders. These shapes naturally distribute the compressive forces of the deep ocean evenly across their entire surface, preventing localized stress fractures. Even with optimal geometry, the metals themselves must be extraordinary. Engineers construct these inner hulls using specialized materials like titanium or high-tensile steel, which are chemically engineered to endure immense compressive forces without buckling. When applied to modern military architecture, these pressure vessels are massive, with steel walls often ranging from several inches to over a foot thick. Hull design prioritizes material geometry and tensile strength over interior space. Everything inside is a compromise, dictated by the physical forces outside. Once the vessel can survive the pressure, it needs to move. The first axis of movement is vertical, controlling descent and ascent. This requires manipulating Archimedes' principle. The upward buoyant force equals the weight of displaced fluid. If the displaced water weighs more, the vessel floats. To dive, main ballast tanks flood with seawater. The downward force now exceeds the buoyant force, and the vessel sinks. Surfacing reverses the process. The submarine forcefully expels that water by pumping highly compressed air into the tanks, reducing the vessel's total mass and restoring positive buoyancy. While main ballast tanks handle the heavy lifting of ascending and descending, smaller internal trim tanks allow the crew to shift water forward or backward, perfectly balancing the submarine's horizontal pitch. Mastering this vertical axis means achieving neutral buoyancy, a delicate equilibrium where the sub hovers weightless in the water column, expending zero energy to maintain depth. With buoyancy controlled, the vessel requires mechanical propulsion to move forward. But doing this underwater means generating vast amounts of power in an environment entirely devoid of atmospheric oxygen. Traditionally, submarines used a diesel-electric system. On the surface, a diesel engine draws air through a snorkel, charging massive battery banks. When submerged, the air-breathing engine shuts down. Propulsion relies entirely on finite battery power, strictly limiting how long the vessel can stay submerged. The solution to this bottleneck was the development of a completely closed-loop energy source, nuclear propulsion. In 1954, the launch of the USS Nautilus marked the exact inflection point where submarines broke their reliance on surface oxygen. Instead of burning fossil fuels, a nuclear reactor generates intense heat through controlled fission. This heat turns water into steam, which drives the turbines that power both the electrical grid and the propellers. The entire reaction requires absolutely zero outside air. Nuclear propulsion eliminated the oxygen constraint. It turned submarines from surface ships that occasionally dive into deep-sea leviathans capable of limitless submerged endurance. Now you have a machine that can survive the pressure, hover at depth, and run indefinitely. But you still face the problem of navigating thousands of miles accurately while completely cut off from GPS. Without external signals, submarines navigate via an inertial navigation system. Sensitive accelerometers and gyroscopes track every microscopic change in velocity. But INS has a vulnerability: measurement drift. Tiny miscalculations compound over time, causing the calculated position to slowly pull away from the actual location. To map the external environment and detect threats, submarines leverage the one physical property that thrives underwater: sound. Sonar comes in two forms. Active sonar emits a sound wave and times the echo returning from an object, which provides precise distance data but reveals the sub's location. Passive sonar is strictly for stealth, using highly sensitive hydrophones to listen for the acoustic signatures of other ships without emitting any noise. Gathering this acoustic data is one thing, but translating it into situational awareness requires highly trained crews to interpret an overwhelming barrage of auditory information. Navigating the deep is a continuous mathematical exercise. It requires leveraging the physics of acoustics and inertial motion to compensate for the absolute blindness of the ocean. When you assemble the high-tensile pressure hull, the precisely tuned ballast tanks, the nuclear reactor, and the inertial navigation systems, the result is an incredibly dense, integrated machine. It is a vessel perfectly adapted to function inside a deeply hostile environment. Inside that sealed hull, the crew's survival depends on advanced chemical scrubbing systems. As sailors exhale, soda-lime compounds continuously bind to and strip carbon dioxide out of the air, preventing lethal toxicity and pressure buildup within the closed-loop atmosphere. This exact integration of life support and physics enables ballistic missile submarines to vanish into the deep for months at a time, providing an undetectable platform for strategic nuclear deterrence. Outside the military domain, these same engineering principles allow research submersibles to safely drop scientists into the ocean's trenches to map the final frontiers on Earth. A submarine does not fight the laws of deep-sea physics. Its entire form and function are dictated by them. By mastering pressure, buoyancy, acoustics, and atomic power, the modern submarine stands as an unparalleled engineering triumph. It turned an impassable, crushing barrier into a sustained operational domain.